Multiple current carrying wires 4. The figure shows an overhead view of a straight current carrying wire. So that's this thing right here at the top. Assume that it is fixed in place. And when we say overhead view, it means like we're above a tabletop and we're looking down on what's happening. Next to the straight wire is a loop which rests freely on a frictionless surface. As shown, current is already flowing by some means clockwise around the loop. We want to use arrows to show the direction of the magnetic force on each side of the loop. To do that, the magnetic force is due to an interaction between a magnetic field and a moving current. The magnetic field created by this straight wire here at the top is going to be directed into the page on this side of the wire. And the further we get from that wire at the top, the weaker the magnetic field. So I've drawn the X's closer together here where we're close to this wire. And as we get further away radially from that wire, I've drawn the X's more spread out to indicate that the magnetic field is weaker. We know that it's into the page on this portion of the circuit because by the Thumbkin twist and right hand rule, if you point your right thumb in the direction that the conventional current is traveling, then your fingers will point, see how they're pointing into the page down here. If we were up top above the wire, then the magnetic field lines would be coming towards us. But down here, they're pointing into the page. In which direction does the magnetic force act on each of these sides of the loop? For that, we need to use the pat-pat right-hand rule, which involves pointing your right thumb in the direction that the current is traveling, and then pointing your fingers, represented by these nails, in the direction that the magnetic field acts. On side A, we've got to point our right thumb towards the top of the page, and then our fingers are going to point into the page. In which direction would the pat-pat end up being? And you can see near the bottom of the screen, right where I'm pointing, there's a force that points to the left here. There you go. On side B, we'll do the same thing. We'll point our right thumb in the direction of the current, which is traveling to the right. The field lines point into the page, and you can see the arrow right by my fingers points to the top of the page. And that goes along with what we said in an earlier video, where if you have currents that are parallel, it's going to be an attractive force between those. So the force on B then would be attractive or upward towards this straight current carrying wire. On side C, we could convince ourselves, I'll let you figure that out, that the force is going to be in that direction. And for side D, you see we have current traveling to the left, which is directly opposite to the current that's going up here. And we said in an earlier video that would be a repulsive force. And you could show that with your right-hand rule as well. On side D, you point your right thumb in the direction that the current is traveling. You point your fingers in the direction of the magnetic field, which is into the page. And way at the right end of the screen, you see the arrow pointing downward, which goes along with what we put here for side D. How do the magnitudes of the forces on sides C and A compare? By symmetry, those are equal to each other. The current through A and through C is the same, and at every point along A and at every matching point along C, there's an identical strength of magnetic field. So those two left-right forces, they exactly cancel each other. However, for sides B and D, they don't cancel. And the reason they don't cancel is because while the current is the same through B and D, the strength of the magnetic field through which that current is traveling is not the same. We said at the outset that when we're closer to this straight current carrying wire, the magnetic field is going to be stronger the closer we are. And then at the location of D, the magnetic field, you see, is going to be weaker. And because of that, the force on B is stronger, which means that this attractive force is greater than this repulsive force So letter D, in which direction will the loop accelerate? That way. Let's do one more. Last time we were up above looking down on a tabletop, and that's not the case here. Here we're standing on the floor, we're looking horizontally, and here's a wire. The ceiling is above us, the floor is below us, and we have this circuit here that we want to just hang in midair. And we know by the diagram that there's going to be current that's going in this sense counterclockwise around this circuit. And we want to know which way should there be a current in this wire up here such that this circuit can somehow hang in space, motionless. Okay, so obviously we need an attractive force here because mg acts downward, gravity. What we need is a magnetic force that exactly is equal to that and opposite. So we need an attractive force. And the deal is we're involving that portion of the loop and that portion of the loop because, as we just mentioned in the previous problem, whenever we have this portion and this portion, those magnetic forces exactly cancel. And we know that the force on this portion that has a resistor with it as well, that's going to be greater than the force on this portion down here because it's closer to the wire. What we want is we want that to be the attractive force. Well, since current is going to the left through that portion of this loop, we know that we want the current in this wire up at the top to also go toward the left. That will result in a net attractive force, which, if we do it right, maybe can exactly cancel this downward mg.